Welcome to Chemistry 111. So continue where we left off. Quick reminder, last week of classes, we're reviewing the basic topics for each chapter. And then if we have some time, we'll go into some achieve homework, but right now we have to continue where we left off. Don't forget, if you're in the Monday, Wednesday, Friday class, final is Wednesday at 12:30. The Monday, Wednesday, Friday class, final is Wednesday at 12:30. The Tuesday, Thursday class, it is on Monday at 3:30. So that's next week. Quick heads up, there is a blood drive on Monday as well. That's on your end too. We're having a review session Wednesday, which is tonight, 7 p.m. in Casa. And there's also going to be one coming Monday and Tuesday, also at 7 p.m. There may be some bonus points showing up, but either way, it's a chance for you to get some help with some homework, catch up on some of that, work on some of your weaknesses before this turning in test 4 or before the final. Obviously, the Monday and Tuesday one are less useful for the Tuesday, Thursday class. And then one last reminder, lab this week is a chance to either make up a lab. If you've missed more than 2, turn in whatever labs you've yet to turn in and do some review. So bring your computer, come get some help. I'll be easily enough to give you the help you need. I'll get whoever needs to get started on a lab started, but then I'll come around and be checking, oh, hey, you're okay, you're struggling with that. Oh, hey, that's where you're struggling with. And so we'll work through those. But that's the plan for Wednesday and Thursday lab. If you don't show up, I'll try not to have my feelings be hurt. So don't worry about it if you're doing fine and you got all the homework caught up with. Sometimes it's better just to relax, just to take a load off for a little bit. Okay, we last left on chapter 6. We finished up at the very end of chapter 6. We talked about that this was the Lewis structure chapter. You wouldn't actually have to draw any of the structures as an answer, but there might be answers where you might have to sketch the thing in order to better answer it. Like if they had a structure of SO2 and they just showed this and they said, how many lone pairs are on the oxygen? Well, that's not really showing up real well. Let's see if the green one's any better. Yeah, maybe. How many lone pairs are on the oxygen? Or how many lone pairs are on the sulfur? What you'd have to do is you'd have to go, okay, sulfur should have 6. You count up all the electrons. You go, lone pair, lone pair. Each oxygen has 2 lone pairs. Sulfur should have 1 lone pair. So there might be a question like that. How many lone pairs are on this atom? There might be a question about what would be the formal charge of the oxygen or the sulfur. In this case, 1, 2, 3, 4, 5, 6. Sulfur has 0 formal charge. Oxygen has 1, 2, 3, 4, 5, 6, 0 formal charge. Ozone, for example. Ozone, if we did that and gave everything an octet, this oxygen on the left would have 0 formal charge because it has 1, 2, 3, 4, 5, 6. The oxygen in the middle would have 1, 2, 3, 4, 5, which is 1 less than its optimum 6. It would have a formal charge of 1. Now this oxygen on the right, 1, 2, 3, 4, 5, 6, 7 would have a charge of -1 because it has 1 over the 6. The net charge of ozone is 0, but the formal charge on the center oxygen is +1. The formal charge of the rightmost oxygen is -1. So that would be an example. You might have to draw it out if they said, what is the formal charge of this atom in this structure? So that's how they might ask something. It might be drawn out for you, or it might be something you have to sketch. But keep in mind, I will give you some sketch paper for that. Okay. Now, the chapters where you really have to draw them would be chapter 7. Chapter 7. So chapter 7 is where we spend a majority of the time on Vesper, the valence shell electron pair repulsion model. So how did this work? We learned about electronic geometry, which is the one that looks at just electron domains. And we looked at molecular geometry. And molecular geometry, which looked at the bonds. So it still cared about the electron domains and the lone pairs, but the geometry was based on where the bonds are. So we ignored the electron domains and just looked at what shape did the atoms itself make. Now, how are those questions going to be asked? They may be questions regarding turning a formula into a shape, or saying from shape to formula. So it could be something as easy as, what is the shape of CO2? What is the shape of CO2? And you'd have to sketch that for yourself. You'd have to say CO2, C, double bond O, double bond O. What shape would that be? That would be linear. What is the molecular geometry? You would say linear. But then from shape to formula, if I gave you say, which of these structures is tetrahedral? Say tetrahedral, and you have to go, you had the option of like CH4 and something like S4 and, let's see, like Cl4, what, like minus or something like that. I'm not going to think of a fourth answer right now, but you might have to sketch some of those out and say, oh, okay, no, that's not tetrahedral. That's not tetrahedral. And so you'd be able to go, which one of these is tetrahedral? So that's what I mean when I say shape to structure. Say, if I give you a set shape, which of these guys would make a geometry that fit that shape? Once again, you will not have to obviously memorize the names, but you might have to recognize what that name brings up. So they'll have options. There'll be multiple choice. It's not a fill in the blank. But you still have to know a little bit about what the heck this tetrahedral look like. There may also be at least a bond angle question. Not much, but bond angle. We didn't go over this too much, but we did it all about that Lewis structure lab, that Vesper model lab. Probably the 3 bond angles you need to know, more likely than not, is linear. Linear is 180. Trigonal planar is 120. And the big one, the only really hard one, is our tetrahedral is 109.5. Our tetrahedral is 109.5. So if it's making up a tetrahedral structure, it's going to be based on the 109.5. If there is a lone pair, it's always smaller than the ideal. But if they show you something like this, like, oh, C H H H O H, and they say, what is this bond angle there? You would go, well, that has 4 things coming off of it. They're all bonds. It's 109.5. But once again, one question at best. One question at best. Okay. We also in this chapter have some ideas about polarity and dipoles. Polarity and dipoles. So, remember, our polarity is when we have 2 guys of very different electronegativity. The big ones are usually O, N, and F. O, N, and F with any other atoms besides their twin is usually polar. So O and F, that's polar. O and S, that's polar. O and Cl, that's polar. Most of those guys are going to be polar, at least a polar bond. But you got to remember, equal and opposite cancel out. So if I said CO2, again, not polar molecule, but polar bond. Why? Because this oxygen counters this oxygen. If I said SO2, it is a polar bond and it is a polar molecule because SO2 has a lone pair on the center of the sulfur. So even though this guy is left of that guy, is left and that guy's right, they're both down. So they're not perfectly opposite of each other. They're not the direct inverse. They're just so that guy would be a polar molecule, that guy would not. But that's what it means. Does this guy have a dipole? If I say, you say, that would say, no, that guy, yes. If I say, why does this have a dipole? It's like, well, this is polar bonds and a polar shape. And that's like polar bonds, but not a polar shape. So there's be a question about those. There'll be a question about some sigma versus pi bonds. Sigma versus pi. Remember, what was sigma? What was pi? Sigma was the single bond / the first bond. Pi was the double bond or triple bond. So this guy, CO and CO2 and SO2 both have 2 sigma and 2 pi. So we have the first bond of the CO to the left, the first bond of the CO to the right. The second bond, which makes the double of CO to the left, the second bond of the double of the CO to the right. If I had something like H, C, triple bond, N, sigma bond, and 2 pi. Because we have a double and a triple bond there. But the first bond between any 2 atoms starts sigma. And then any bond after that is pi. And finally, hybridization. Hybridization. What was that? Hybridization. That was our SP, SP2, SP3. Remember, the shape is dependent on the hybridization, or the hybridization is dependent on the shape. Basically, the number of electron domains relates to the orbital. 2 electron domains means sp. 3 electron domains, sp2. 4 electron domains would be our sp3. So HCN is sp. CO2 is sp, but SO2 is sp2 because it has 1, 2, 3 electron domains. That lone pair counts as electron domain. But that is stuff you can expect from chapter 7. So we don't have to do any of the bonding versus anti-bonding molecular orbital theory, which I kind of went over very briefly, but it's super complex. And so we don't have to worry about that at all. Now, chapter 8. Chapter 8 was a short chapter as well. Not a particularly hard chapter, I hope. Okay. So, chapter 8. One thing we talk about in chapter 8 is electrolytes. Lights and kind of strong versus weak acids. Versus weak. Both strong versus weak electrolytes and strong versus weak acids. The basic idea here is strong electrolytes and strong acids, and then of course we had non. When a thing dissolves, strong, 100% dissociation, breaks apart. Weak would be like, I don't know, 20% breaks apart. And non would be 0%. So weak acids, remember when we did the our net ionic equation, they did not break apart in the net ionic equation. Strong acids did. So another thing we did in this chapter and expect to answer at least one question is balancing chemical reactions. Not hard. Hopefully you can get that question. Hopefully you'll at least have one question out of 70, balancing chemical reactions. Of course, hopefully you'll have a lot more than just one, but that should be a give me. Just make sure, remember, whole numbers. We want whole numbers, simplest whole numbers. But, okay. And then net ionic. Turning complete reaction to a net ionic. This is not as hard as it sounds. You got to remember 2 things. Solids and liquids don't break apart. And neither do. And then no weak electrolytes either. So, if, for example, just give a couple one. Silver nitrate aqueous plus sodium chloride aqueous goes to silver chloride solid plus sodium nitrate aqueous. Given this equation, could you figure out the net ionic reaction from there? Hopefully the answer is yes. It's not asking you to figure out, is this soluble? It's telling you this is not soluble. So everything that was soluble would break apart and get canceled out. nitrate, nitrate, sodium, sodium. So the net ionic would be Ag plus aqueous, and chloride minus aqueous goes to AgCl, solid. If I had an acid like HNO3 aqueous plus sodium hydroxide aqueous goes to water and a salt, NaNO3 aqueous. Hopefully those cancel out and you would have H plus and OH minus goes to water. The only one that could be tricky if you had a weak acid like HF. HF would not break apart. So you'd have HF plus OH minus goes to water and F minus. That's the only way they could really make that trickier than that. I'm not sure they did, but I got to throw that in there. And the last topic that we'll expect to see in this chapter is oxidation reduction. So redox. Oxidation is losing electrons. Reduction is gaining electrons. So you might be asked something like, which atom is oxidized in this chemical equation? You might also be asked to calculate oxidation state. So if I gave you something like CrO4 1 minus, what is the oxidation state of chromium in there? Well, you have to go, each oxygen is 2 minus. 4 oxygens are 8 minus. So -8 equals negative plus chromium equals -1. So some number minus 8 is -1. That some number has to be +7. So chromium is +7 in chromate. So you might be asked to do something like that. You might be asked to go chromium, let's see, like chromate goes to chromium 3 plus. I'm not balancing this guy, but say silver. Silver goes silver plus. And you have to go, which one of these guys is being oxidized? Well, the oxidized guy ends up losing an electron. And the reduced guy gains an electron. So chromium's going from 7 plus to 3 plus. It's gaining 4 electrons. Silver is going from 0 to +1. So it would be losing 1 electron per silver. Now that's not balanced in the least. It's made balanced electron-wise. But so that's what would be asked of Chapter 8. Not a ton of stuff. Now 9, 10, 11, especially 9 and 10, play a rather big part of the thing. So keep in mind, all of the ones that ask you to turn grams to moles to moles to grams, they will give you molar masses. You have to set them up. You have to be able to set this up. So if this is what you're struggling with, this is a perfect thing to work on in lab today or tomorrow. If you have trouble setting these up, because they will give you the molar masses. But okay, so Chapter 9. Chapter 9, one of the first major things we learned in the stoichiometry chapter is grams to moles to grams. And we learned grams to moles to molarity. be able to do those two things. That is a good thing to be able to do. You should also be able to do molarity to moles to atoms. All these are just extensions of everything we can do. This, if we know how to set this up, it should be straightforward. We should also be able to go molarity to moles to moles to molarity. A modified version of this is just a dilution problem. Modified version of this is just a dilution problem. So we have dilution problems. We'll have a few limiting reagent. When we do the limiting reagent, please note, they will make those easier. They do make those a lot easier in that they try to make this, like if you look at it on an atom per atom basis or a mole per mole basis and said, okay, you have a reaction that looks like this. Zinc plus oxygen goes to zinc oxide. And if they said, we have, here's the zinc atoms, and we have the O's. What would the ending solution look like? What would the ending solution look like? Well, for every zinc atom, we would consume one. For every 2 zinc atoms we have, we would consume 1 O2. We happen to have 4 zinc atoms, so we'll consume 2 O2s. So the ending product would look something like this. Yeah. So we'd have 4 zinc oxides and 1 O2 floating around left. So that's an example of how they could ask a limiting reagent problem without making you do a ton of math. So they can make that a lot easier. But there's also, finally, besides the limiting reagent, there's also percent yield. They could go from, which percent yield is, percent is equal to actual divided by theoretical times 100. They could go from, they could make you either calculate the percent yield, or they could go from the percent yield and actually have you calculate the actual yield. Either one, you still have to go grams to moles to moles to grams from our starting reagent. So let's look at some problems. Let's set some of these guys up. I'm just going to make these up off the top of my head, doing my best to try to say these. If I dissolve 35 grams of aluminum oxide in 55 mils solution, what is molarity? Molarity. And then they would say the molar mass, they'd say aluminum oxide, molar mass is 102 grams per mole. They'll give you that. So you'd have all you need, and there'd be 4 possibilities. So what you'd have to do, you'd have to solve that. So how would you solve that? It's we convert each time. So we start with our 35 grams. The next thing we need to do is get into moles. So we divide by my molar mass because 102 grams per mole, grams on top cancels grams on bottom. Next, I would divide by my volume in liters because molarity is a mole per liter. That's the only one that's not necessarily abundantly obvious. We have to divide by our volume in liters because molarity is moles per liter. So if I have moles, I need liters. So since it's 55 milliliters, I divide by 0.055 liters. And the units would be moles per liter or molarity. So that'd be just a perfect example of something that could be asked. Perfect example of something that could be asked. Just so 35 divided by 102 divided by 0.055. 6.238. So the answer would have been 6.238 in this situation. They could do a dilution problem. You just have to reason her out. If a 25 mil solution of unknown acid is diluted to 85 mils to give a final concentration, final molarity of 0.113. What is the original molarity? That's a perfect question for dilution. So what do? M1V1 equals M2V2. It's the idea of molarity to moles to moles to molarity. The volume, the amount of our acid does not change, just how much is dissolving it. So 25 times our M equals 85 times our 0.113. So what do we have to do? We have to divide both sides by 25 to get our old molarity. That's a perfectly reasonable 0.113 divided by 25 times 85. So we'd have the original concentration was 0.3842. So M is 0.3842. So let's see if this one works any better. The marker's kind of dying on me. Now, given a quick example of just a percent yield one. Let's see. As I said, we could be given either the percent yield and find the actual yield, or the actual yield and find the percent yield. If, got to think of something I know. Sure. If N2 plus, let's see. Okay. If this reaction goes off with, let's say, 35% accuracy, 35% efficiency. If we have 35% efficiency, how much NO3 can be made with 40 grams oxygen? O2. An abundance of nitrogen. 40 grams oxygen. So they'll give you oxygen molar mass is 32. 48 plus. And NO3's molar mass is I think 62 grams per mole. So what would we do? We turn grams of oxygen to moles of oxygen, moles of oxygen to moles of nitrate and nitrogen trioxide, and moles of nitrogen trioxide to grams of nitrogen trioxide. So 42 for every 3 moles of oxygen, we need 2 moles of NO3, and for every 1 mole of NO3, it's 62 grams. So doing that first step figures out my theoretical yield. They would give you, as I said, the balanced chemical equation. They would give you the molar mass. So 40 divided by 32, 3 times 2 times 62. You'd get the molar mass. The mass of this would be 51. That's 51.7 is the theoretical mass. If this is 35% efficient, 51.7 times the 35%, so 0.35, you would get 18 grams. So that's an example of a perfectly reasonable question about percent yield. But those are examples of problems from chapter 9. So be able to do these conversions, be able to do these. This is going to be something that will be asked of you on multiple problems. So don't be surprised when you get a big chunk of these questions. Chapter 10. Chapter 10 also plays a pretty big part, honestly, partially because in second semester, we will be looking at thermodynamics again. We'll be looking at this stuff again, so they want this to be fresh, not be something that we just immediately forget. So chapter 10, we need to be able to look at Q equals MCAT. So the heat flow equals the mass times the specific heat capacity times your change in temperature. They could be asking how much heat does it need to change this temperature. They could be asking what is the specific heat capacity of this object given this heat flow and this temperature change. They could even ask you how much does this object weighs based on this heat flow and temperature change. So hopefully you were there for the second to last lab and got to at least practice that stuff, because that lab is good practice for this material. You need to recognize endo versus exothermic. Endo, it's positive delta H. Exo, it's negative delta H. Heat is exiting versus heat entering. Endothermic reaction absorbs heat. Exothermic reaction, heat is released. Heat is a product versus heat is a reactant. And also be able to recognize the definition of delta H of formation. What does it mean to calculate? Definition, how to calculate. How to calculate. So this you can find in the book. It's pretty easy once you understand what it is, but I can't really give you any more hints than if you know what it means to calculate the delta H formation, it's an easy problem. If you don't, you're just going to guess, and you might get it right, you might get it wrong. There's a lot of stuff about delta H of reaction, either how to calculate it or using our example. So remember, delta H reaction is delta H of the products minus delta H of the reactant. So we have to sum them all up. Sum of the products minus the sum of the reactants. And we have to count for all the samples of that. Then there will also be something about Hess's law. Once again, the Hess's law problem is not supposed to be super hard. Not supposed to be super hard. It's supposed to be like, oh, I maybe flip this around and double it. I'm going to be dealing with 2 equations, not like 3 or 4 equations. But you still need to understand Hess's law. And there's one last thing. We didn't really go over this too much, but phase changes. Phase changes. When we change phase, when we go from liquid to solid, or solid to liquid, or liquid to gas, gas to liquid, or boiling or condensing, melting or freezing. There's some interesting things about that. There's a Q equals MCAT to heat up a liquid or cool down a liquid. But when it comes to phase changes, we have a different setup. It is a direct delta H. And because of that, this delta H, we do not actually change temperature while we are undergoing a phase change. While we are melting something or freezing something, the temperature remains constant. So the whole idea of why do we put ice into a beverage is so that as that ice melts, it will chill down the beverage to the temperature of the ice, which is ideally 0 degrees. Until all that ice melts, the beverage will stay that temperature. It will stay cold as long as there is ice in solution. When it cannot heat up until it completely melts. In the same way, when you boil a liquid, the temperature will stay at 100 until all the liquid is boiled, which is why if you're, like, say, cooking spaghetti, you maybe crank it up at first to get it to boil, but once it's boiling, you can lower the temperature a bit. You don't need to be heat. You can lower the heat a bit. You don't need to be pumping temperature in because the water can't get hotter than 100 degrees until it becomes all steam. And we're not going for steamed spaghetti. We put it in a boiling pot. But so those are some of the, I'll go over some of these in a minute, but I want to make sure I get through chapter 11 real quick. Chapter 11 probably plays the lowest part, one of the lesser parts of this final. There is a few chapter 11 questions, but not a whole lot, considering we spent as much time as we did, because we will not really talk about gases too much. One of the things we need to know is the ideal gas understanding. What is gas understanding? What are the laws? How do they relate? So if I asked you, if I increased my pressure by a factor of 2, I doubled my pressure, what would happen to the temperature at a constant volume? Well, the temperature should double. If I doubled my pressure, what should happen to the volume? My volume should half at a constant temperature. That these guys are directly proportional, these guys are indirectly proportional. There is maybe one PV equals nRT equation. There's maybe one. So yes, it may be easy. We may have prepped vigorously for this test 4, but there's only one PV equals nRT on the final. So don't be like looking like, oh, I can do this like the back of my hand. This is going to save me. It's like, no. There's maybe like one question about kinetic molecular theory, which kinetic molecular theory, remember, had to do with gases moving fast and how the heat makes them move faster and why the speeding up of the gases resulted in a higher pressure and all that stuff. There wasn't too much. Look over those slides again to get a good gist of it. And there's maybe one effusion question. Remember, effusion was the rate of one gas over the rate of a second gas equals the square root of the molar mass of the second gas over the molar mass of the first gas. Pretty much straightforward. However, since they won't be giving you that equation, you might have to guess if you don't remember that equation. But once again, it's not a huge part, but typically this number should be greater than 1. Should be greater than 1. Okay, so that is all the material. Yes, there's maybe 1 or 2 questions on the final that we didn't really go over. Unfortunately, that's the nature. We squeaked through. We got through chapter 11. We don't really have any time to go into chapter 12, or anything like that. So there may be stuff that we just don't really cover. But I think we covered a good deal of this, at least the briefest of briefs. Okay, let's do 1Q equals MCAT real quick. 1Q equals MCAT real quick. Just to end this off. So if let's see, this is maybe the hardest thing they could throw at you. If I had metal at 100 degrees, see, with specific heat of, let's say, 0.38 joules per gram C, and I put that into 50 grams of water at 22. You see, specific heat at 4.184. When I put them together, the final temperature, the final temp is 33 degrees C. What is the mass of the metal? What is the mass of the metal? We want to know mass of metal. So this is the hardest thing they could throw at you, and I doubt all of them are going to be like that. There might be one. I don't remember. I've been looking at a couple different finals. So this is the hardest that I've seen between those. So the heat of the water, Q of the water, is 50 times 4.184 times the change in temperature. 33 minus 22 is 11. So the Q of the water is 50 times 4.184 times 11 is 2,301. 2,301. Now the metal is, the Q of the metal is equal to my mass times my specific heat, which is 0.38, times my delta T. 100 minus 33 is, what, 67? So I'm going to take my 2,301, divide by 67, divide by 0.38, and you would have the mass of the metal, which is like 90.4 grams. So 2,301 divided by 67 divided by 0.38 gave me 90.38. So that is the hardest thing they could throw at you. The absolute hardest thing they could throw at you with Q equals MCAT. Not going to be, you'll probably see a much easier one where here is the heat, here is the mass, here's the change in temperature. What is your specific heat capacity? Or here's your specific heat capacity, here's your mass, here's your change in temperature. How much heat flow? Okay, so that is all we have time for today. That puts us to 10:50. Thank you for trying to pay attention. And on Friday, we'll look at some more homework. So we'll look at some homework. So if you have any particular questions, bring them to me. Otherwise, I will just go through ones at random.